Hello everyone, this is Mr. Kaviani, and in this video, we're going to explore Newton's universal law of gravitation. By the end of this video, you should be able to calculate the force of gravity acting between any two objects, approximate a numerical value of the gravitational field near the surface of an object, and use Newton's second law and circular motion equations to solve problems involving orbital motion where gravity acts as the centripetal force. To begin, let's define Newton's universal law of gravitation. Newton defined gravity as an attractional force between any two objects with mass, not just objects on Earth and our Earth. What this means is that every object in the universe exerts a gravitational force of attraction on every other object. Now, realize that this force is proportional to the masses of the two objects involved and the distance between their centers. So as we get further and further away from an object, the effect of its gravity is weaker and weaker. It's also important to note that because this is an interaction between two objects, the force that one object exerts on another is equal to the force that that object exerts on it. So for example, if you have two spheres, M1 and M2, shown on the screen here, M1 is attracting M2 towards it. But M2 attracts M1 towards it as well, right? And the force that they each attract each other with, this F1 and F2, are identical, right? And so even though the mass of M1 is greater, they exert an equal force on each other, right? This is a product of a Newton's third law pair interaction, right? If M1 exerts a force on M2, it must be equal in magnitude and opposite in direction to the force that M2 exerts on M1. So to express this in an equation that we'll be using a lot in this unit, we can say that the force of gravity between any two objects is equal to something called big G, which we'll get to in a moment, multiplied by the product of their masses divided by R, which is the distance between their centers squared. A couple of key things to point out. The universal gravitation constant is an experimentally determined constant from experiment here on Earth. The value of this is 6.6743 times 10 to the minus 11, and the units are in meters cubed, kilogram to the power of -1, and second to the power of -2. I know those units look very strange. The reason it has those units is so that when we multiply two masses and divide by a distance squared, we get a Newton. And so you can make this work for yourself. M1 is the mass of object 1, M2 is the mass of object 2, and again, R is not a radius per se, but it's the distance between the centers of the two objects. And I want to make sure you realize this is the center, from center to center. So for M1, it's the middle of M1, all the way to the middle of M2. This will be incredibly important when we're solving problems, as you'll often sometimes just be told the distance between the object's surfaces and not strictly the distance between their centers, which we'll have to calculate. So once again, this is how we calculate the force of gravity acting between any two objects in our universe that have mass. Let's do a quick example problem involving calculating the force of gravity between two astronauts in space that are 3 meters apart. If each astronaut has a mass of 75 kilograms, let's calculate the gravitational force of attraction between them. In other words, the gravitational force that one astronaut exerts on the other, and therefore the same force that the other astronaut exerts back on that first astronaut. So to solve this, we'll use our formula, plugging in the values for the masses of the astronauts and the distance between their centers. In this case, we're assuming that this is the center-to-center distance. All right. Now, whenever I multiply two numbers together and one of them is in scientific notation, I like to make sure the other one is also in scientific notation. And so this one's fine as it is, right? This number right here, this quotient, will be equal to 625, which is also the same thing as 6.25 times 10 to the power of 2. So then in my calculator, I would do this. I would do 6.6743 times 6.25, and that would all be multiplied by 10 to, in this case, we're multiplying together, so we'll add the exponents, -11 plus 2. And I already know that my answer will be something around, here we go, 10 to the power of -9 or -8, looks like. All right, that's 41.7 times 10 to the power of -9, but again, this is not in scientific notation in standard form, so I'll move this over left one. If I go left, I made the number smaller by a factor of 10, so I'll make the exponent here. I'll increase it by 1, so from -9 to -8. So that would be 4.17 times 10 to the -8. And I just checked myself. Let's see. It was 41.7. I made it smaller. I made the exponent then more positive, or 1 in the more positive direction. So there we go. That is 4.17 times 10 to the -8 newtons, because we are measuring a force of attraction. So let's calculate the acceleration of either astronaut. The reason I'm asking you to do this is to realize that, yes, even though we all exert a force of gravity on each other, it doesn't have a noticeable or really significant effect, and we'll see that here in a moment. To solve for the acceleration of the astronaut, let's assume that the only force acting on them is the force of gravity produced by the other astronaut. That would mean then that this would be their net force, essentially. So the force of gravity acting on them would be equal to their mass multiplied by their acceleration. So in other words, their acceleration would be this force of gravity we just calculated divided by their mass. So this would be 4.17 times 10 to the -8 divided by 75 kilograms. And you can always just write this as 75 times 10 to the power of 0 if it helps. Any number is times 10 to the 0, or times 1 essentially, which would be equal to, right, this in my calculator gives me 0.0556 times 10 to the -8. And so if I just move the decimal place over 1, 2 to the right, and I'll make this 2 smaller, that would be 5.56 times 10 to the -10 meters per second squared. Okay. Now, as you can see, that is an incredibly small acceleration value. And so even though these two astronauts are very close, we're not going to see one astronaut start to accelerate towards the other solely based on their gravity alone. Let's see how this applies, though, to much larger bodies. All right, let's say you were trying to calculate the gravitational force of attraction between the Earth and our moon. The mass of the Earth is 5.98 times 10 to the 24 kilograms, and the mass of the moon is 7.26 times 10 to the 22nd kilograms, respectively. The distances separating them is 3.84 times 10 to the 8th. That is surface to surface, not center to center. We're also given the radius of the Earth and radius of the moon. We can apply the same formula as we have before. Now, in this case, we were given the masses directly, but we were not directly given the center-to-center distance. If we draw a straight line between the center of the Earth and the moon, we'll see that the r value here, or the distance between their centers, can be solved by adding the distance and the two radii. Here's how that would look. I've gone ahead and sketched that. To the right, how we can show that. That would also mean then, algebraically, that r would be equal to the distance I was given, 3.84 times 10 to the 8th, plus each radii. So the Earth was 6.38 times 10 to the 6th, and the moon was 1.74 times 10 to the power of 6. So that is our r value, or the distance between the centers of the two objects. So before I do anything, I'm going to get my r value as one number in scientific notation. And to do that, I will use my knowledge of adding numbers involving scientific notation. I will convert the 3.84 to the power of 10 to the 6th here, because I already have two numbers whose exponent is 6. So to do that, to make the exponent 2 times smaller, I will make the number 2 times, or 2 places of 10 bigger. So then that means that would be r is equal to 384. And once they're all in the power of, to the power of 6, I can add them together, plus 6.38 plus 1.74, and all of that will be times 10 to the power of 6. And that is equal to directly 392.12 times 10 to the power of 6, but I'll go back here 2 places back. That'll be 3.9212 times 10 to the power of 8 meters. Okay, now that we've gotten our r value, or distinct distance from center to center value, I'll go ahead and plug in all my values to the FG equation. That would be equal to 6.6743 times 10 to the minus 11. This constant will always be given to you, by the way. Multiplied by the mass of the Earth, the mass of the moon, and divide all of that by r squared. Wow, that's a lot of scientific notation. Now, don't worry, it's not that bad. Here's how I encourage you to break this down to make it simple and easy to solve without involving the use of your calculator too terribly much. Since the g is outside the fraction, I can bring that into the numerator here. G is just g over 1, right? So I'll just go ahead and put g in the numerator, and then the only thing I have in the denominator is the r squared value. So I'm going to do one thing here. I'm going to multiply out the whole numerator together using my knowledge of scientific notation, and then I will do the r squared. Then I will just divide the numerator by what I got for r squared to make this easy for me to solve. So the numerator, right, so I'll just say the numerator here would be 6.6743 multiplied by 5.98 multiplied by 7.26, right, all that together, times 10 to the power of, and then again, you'll add the exponents here because we're multiplying, negative 11 plus 24 plus 22. And so that is equal to 289.8 times 10 to the power of 35. And this again, for right now, we're not going to worry about the units. Okay, so then my denominator, right, was that 3.9212 times 10 to the power of 8th squared. And so that's the same thing as saying, and that's equal to 3.9212 squared times 10 to the power of 8 squared, which is 15.376 times 10 to the power of 16, 8 times 2. In this case, I don't really need to convert these to standard scientific notation because I'm going to use them for calculation. FG in this case would then be equal to, again, the significance, so 289.8 divided by 15.376, and that would be equal to, or multiplied by 10 to the power of division here, so we'll subtract the exponents. So if I put just this part into my calculator, I will get 18.85 times 10 to the power of 35 minus 16 is 19. So this will also be equal to 1.885, right? Made it, if I do this 10 times smaller, so that would be one more exponent there. So 10 to the 20 newtons. And that is the strength of the gravitational force of attraction between the Earth and the Moon.